Before we proceed to the nuclear reactions, we must remember that there are conservation laws that are observed in these nuclear reactions. So these are the law of conservation of energy, the law of conservation of mass number, and the law of conservation of electric charge. So in law of conservation of energy, the mass remains the same all throughout a radioactive process or nuclear transformation. Now, you might be asking, it's the law of conservation of energy, but why are we talking about the mass? Because in nuclear chemistry, the E equals mc squared formula applies, meaning mass can get converted to energy and energy can get converted to mass. That is why for nuclear reactions, this law of conservation of energy can also actually be called law of conservation of mass. Essentially, the total mass before and the total mass after should be equal, and the total energy before and the total energy after must also be equal. It means both mass and energy are conserved. Okay? Or you might observe that the mass are not equal before and after, but you must be able to account for the lost mass by some energy involved in the process. It means that the lost mass was actually converted to energy. Okay? And the last two are pretty self-explanatory. So your mass number remain unchanged in nuclear reactions and also electric charges. So let's start. The first radioactive process that is everyone I think is familiar with is the alpha decay. So in the alpha decay, or first, let's talk about what alpha particles are. So in alpha decay, alpha particles are released from the nucleus. Okay, an alpha particle is composed of two neutrons and two protons. So it's like the nucleus of a helium atom. That is why it is often represented by the symbol of helium. But take note that this is not a helium atom, but this is an alpha particle. Okay, it's just the nucleus of the helium atom. This alpha decay is often observed in nuclides with very high mass numbers and very high atomic numbers. And they undergo alpha decay because it decreases their mass numbers by 4 and their atomic numbers by 2. So in one step, they can immediately decrease their mass number and their atomic number. So this is your alpha decay. So example, you have a radon 222. This is a radionuclide that decays through alpha decay. So determine the nature of its daughter nuclide. And now we have to apply what we learned or saw how to write your nuclear reactions. So you have your parent nuclide, radon 222. So it undergoes alpha decay. So definitely you have an alpha particle getting released. Now we need to identify the atomic number. So 86 minus 2, that's 84. And we need to identify the mass number. So that's 222 minus 4, that's 218. So which element has the atomic number 84? Were you able to remember? So the element with an atomic number of 84 is polonium. Okay. Now, let me just share some info about radon 222. So radon 222 is a radioactive gas that escapes to the environment from rocks or soil containing radium 226. In fact, we have seen the radioactive series or decay of radium 226. So in the first step, it releases radon 222. Now, radon 222 being radioactive, if it gets concentrated in a very small area, it can actually be dangerous. So, if you have a small amount of radium is actually present everywhere. So, there's natural radioactive radon present everywhere. Now, the problem is if it gets concentrated in a very small space. So, um, in houses, okay, it is actually important for engineers to inspect the amount of radioactive radon inside the house because it's possible that from the soil down under the foundation of the house, there's actually um, a relatively higher amount of radium 226, for example, releasing radon 222. So it is important that this hazard be known, okay, and be dealt with. Okay. So again, your alpha decay occurs with radionuclides whose atomic mass number is greater than 150. And one important fact in alpha decay is that the energy of the emitted alpha particle is fixed for a given parent nuclide. So for example, in radon 222, in its alpha decay, the kinetic energy of the alpha particle released is 4.78 mega electron volts, and this is constant. So if we consider, for example, the alpha decay of radium 226, if you notice, that's an alpha decay, right? Forming radon 222. Okay, the alpha particle released in this alpha decay. So I'm talking about the first step, which is radium 226 undergoing alpha decay to form radon 222. So for this one, it's the same. It releases alpha particles, but these alpha particles will have a different kinetic energy than the alpha particles produced from the alpha decay of radon 222. So they are both alpha particles, but their kinetic energies will be different. But as long as you have radon 222 as the source of your alpha particles, you know that the kinetic energy of these alpha particles is 4.78 mega electron volts. Next, we have what we call isobaric transition, or the most common is beta decay. So there are actually three processes under this isobaric transition. So the correct term is isobaric transition. Okay. Now, do you recall what isobars are? From the previous video, your isobars are those atoms with the same mass number. So we have three types of isobaric transition. We have the beta decay or the electron emission. We have positron emission and the electron capture. So let's go through these one by one. Let's go to beta decay or beta emission. Okay. In beta emission, so this is the general thing that is happening. So you have the parent nuclide and you have the daughter nuclide whose atomic number is now increased by 1, right? And you have an electron that is released. Now, this electron released, where does this come from? So this comes from the conversion of a neutron represented by this. This neutron gets converted to a proton and an electron, which is represented by the beta symbol to signify that this is an electron originating from a nuclear reaction. So again, You have a neutron, which sort of disintegrates into a proton and an electron. That is why your atomic number increases by 1. So your daughter nuclide has an atomic number greater by 1 unit than the parent nuclide. Okay? Now, in the process, you have an antineutrino that is also emitted. Okay? So the neutrino antineutrino thing, this was they were brought up or they were conceptualized to account for the energy difference in the reaction. So again, we will not deal with these neutrinos and antineutrinos. We are more concerned about the conversion of your elements in these nuclear reactions. So again, in beta decay or beta emission, your mass number remains the same, but the atomic number increases by 1. And in the process, you release an electron, or we call it beta particle, and an antineutrino. So if you see a bar here, that's an antineutrino. So you see here several examples of your beta emission or beta decay. Okay. Now you see why this is called isobaric transition, right? Because the mass number remains constant. Okay. Now, here's a note on the electrons or beta particles emitted in this type of radioactive process. Okay. The beta particles that are emitted have varying kinetic energies. Okay. And this is because um, so you have energy released, right? And the energy released, so that is in the product side, the energy released is actually the sum of the energy of the beta particle and the energy of the antineutrino. Now, the way that your beta particle and your antineutrino shares this released energy is random. Okay, so if they share 50-50, then they share 50-50. In another radionuclide, the electron gets 75% of the energy and the antineutrino gets 25%. So, again, the energy of the beta particle varies. And we have what we call a beta spectrum or a beta particle spectrum. So, this spectrum shows the range of the energies of beta particles emitted from a specific radionuclide. And on the y axis, we see the probability of each energy value. So we have the maximum beta particle energy, which is the highest, okay? And we also have the average or the mean beta particle energy. And of course, we have the highest value of, or the highest probability of energy for your beta particle emitted. Now, this beta spectrum is actually very relevant um, in applying radionuclides in hospitals. Sorry. So the average energy of beta emitting radionuclides administered to patients is important. And for us to get this average energy, we must know the shape of the beta particle spectrum, right? But if we are not after high accuracy, okay, we are not for highly accurate computations, then to get the average beta particle energy, you just get your maximum beta particle energy and divide this by 3. Okay, that is the way to estimate the average beta particle energy. So why is this energy important in administering these radionuclides to patients? Of course, because we want to minimize damage from these radionuclides. So we want to keep the damage at a minimum and just achieve the right level of energy for whatever purpose the radionuclide is being used. Okay, next, we have the positron emission. So in the positron emission, this time, okay, you have a proton which disintegrates into a neutron and a positron. So the positron is just like your beta particle, only with a positive charge. It's like your proton to the electron. Okay? So, since you have a proton disintegrating, the result is that your daughter nuclide has an atomic number which is less than 1, okay, or is lower than the atomic number of your daughter nuclide. So you have there Z minus 1. Okay, and then of course you have a neutron there. So the mass number doesn't change. A proton gets disintegrated, but a neutron is born, so the mass number still remains the same. Okay, and the positron here, the positive charge here, that balances out, right? So you have one here for the proton, and you have one here for the positron. You have one here for the mass number from the proton, and one mass number due to the neutron. Okay, here are some examples of positron emission of some radionuclides. Okay. Now, just like in your beta particle emission, again, the kinetic energy of the emitted positron varies. Now, instead of an antineutrino, a neutrino is released in the positron emission process. Okay. So your neutrino is like the positron to your uh, beta particle. So the neutrino is partnered with the antineutrino. So they are particles with the same properties but just opposite charges, something like that. Okay? So one note here, the mass of the parent nuclide should be greater than the mass of the daughter nuclide by at least 1.02 mega electron volt. So what is this 1.02 mega electron volt? So this value is twice the mass of an electron. Okay, so the mass of the parent nuclide should be greater than the mass of the daughter nuclide by at least twice the mass of an electron. So why is that? So we only see one electron here, or we can only account for one electron, right? So why is it that the mass of the parent nuclide must be greater by twice the mass of an electron? So it's because the mass of a nuclide, okay, includes the mass of the electrons in the orbitals associated with the nucleus. So our parent nuclide here will have the mass of Z electrons, right? Whereas in our daughter nuclide, you only have the mass of Z minus 1 electrons, right? Furthermore, you have a positron, which is a positively charged electron created from the nuclear energy of our parent nuclide. So, in essence, the process sort of loses two electrons, which is why to account for the two electrons lost, the mass of the parent nuclide should be greater than the mass of the daughter nuclide by at least twice the mass of an electron. Okay? And the last isobaric transition is called the electron capture. So the electron capture is quite different, okay? What happens is that you have the nucleus of your parent nuclide snatching an electron from one of your innermost orbitals. Okay, so you remember we have letter designations for our orbitals. So you have your nucleus here, you have your k orbital, you have your l orbital, and you have your m orbital. So the nucleus can snatch an electron from the k from the L, or from the M orbital. Of course, the one which can occur with the highest probability is from the K orbital, followed by the L, and the one with the least probability is the electron from the M orbital. Okay, so that's why it's called electron capture. Now, what is happening in an electron capture? So you have an electron, right, captured by your nucleus. This combines with the proton. Oh, this combines with the proton, forming a neutron, right? So that is why you have in your daughter nuclide an atomic number that is less by 1 unit. So the number of protons decreases by 1 because it is used to create a neutron. Again, your mass number remains the same. And in this process, you also have a neutrino that is released in the process. So here you see some examples of electron capture by some nuclides. So don't mind the notes here. I just forgot to delete them. They were copied from the previous slide. So this one, disregard. Okay, so those are what I want to mention about electron capture. Okay, so those are your isobaric transitions. Now let's go to isomeric transition. Okay, what is an isomer? You probably know isomers from your organic chemistry class, but in nuclear chemistry, we also have isomers. And an isomer is a nucleus that is in an excited state. So you remember the metastable state? Okay, so let's go back to that slide. Here, okay, so you have this metastable indium 113 and the stable indium 113. These are isomers. Okay, so the only difference is that one of them is in an excited state. Now, an isomer can decay because since it's in an excited state, it can release the excess energy. So there's decay that can happen there. So there are two possible ways for this decay to happen. The first one is through high energy photon emission, or what is commonly known as gamma radiation or gamma emission. So you have the excited state nuclide releasing gamma rays and being transformed into the stable isomer. So gamma rays are electromagnetic radiation with very high energy, greater than 100 electron volts. So these are actually, yes, they are photons, okay? They are made of photons, just like your X-rays. They in fact interact with matter in the same manner as X-rays, provided these X-rays have the same energy as that of a gamma ray. So the difference is the origin. So your gamma rays come from your isomers, right? Meanwhile, your X-rays come from electronic transitions in an atom. See the difference? Gamma rays are photons released due to a due to an excited nuclide, or a nuclide in an excited state. X-rays are also photons that are released from electronic transition. So basically, you have an electron in an excited state, they go back to their ground state, photons will be released. That's your X-ray. Okay? Now, another way by which isomeric transition can take place is through internal conversion. So, in internal conversion, what happens is that you have an electron from one of your inner orbitals getting knocked out of the atom. Interesting, right? So in this process, instead of the excess energy getting emitted as gamma rays, the excess energy is transferred to an orbital electron. Again, either in the k orbital, the l orbital, or the m orbital. This is another example of a direct interaction of the nucleus with the orbital electrons revolving around the nucleus. So um, we've seen the first one, which is electron capture, right? So this is the second time that we see a nucleus interacting with orbital electrons. Now, whenever you have a vacant position here, because the electron is either absorbed through electron capture or knocked out through internal conversion, this vacant position is filled by an electron going down, an electron in a higher orbital going down to this vacant position. Okay? Now, in a specific population of a radionuclide, to be specific, a nuclide that is in an excited state. So if you have 100 molecules or 100 nuclides in an excited state, not all of them will undergo the same way. Not all of them will release gamma rays, nor will all of them release or undergo internal conversion. So in fact, a fraction, a fraction of um, what do you call this? A fraction of atoms will undergo gamma radiation, release of gamma radiation, while the remaining atoms will undergo internal conversion. And there is um, a quantity that is called coefficient of internal conversion for a nuclide that is in an excited state. So this is a fraction. So you have in the numerator the total number of electrons emitted, and in the denominator the total number of gamma rays emitted. Okay. So for example, if this value is equal to 1 over 5, okay, 1 over 5, it means that out of 6 decays, one of them will be through internal conversion, while 5 of them will be through gamma radiation or emission of gamma rays. Okay? Now, it is important to note that we have the coefficient of internal conversion for the K conversion, meaning an electron gets knocked out from the K orbital. We also have the coefficient for the L conversion and for the M conversion. So you have for the total coefficient, just the sum of these three. Now, most commonly, it's just the IC that is given, okay? The total coefficient for the internal conversion. So there are some computations that you can perform using this quantity. So for example, if you have 100 decays of an excited nuclei, then following the given, if IC is equal to 1 over 5, it means that you have 5 over 6. This is the fraction, right? 6 is the total. That's 1 plus 5. 1 plus 5. That's the total. We multiply this by the total number of decays, then it gives us approximately 83 decays which undergo via emission of gamma rays, while the remaining 17 decays will undergo through internal conversion or knocking out of electrons from an inner orbital. Okay? So those are your radioactive processes. So we have the alpha decay, the isobaric transitions, which include your beta particle emission, positron emission, electron capture. And we also have our isomeric transitions. We have two types of isomeric transitions. emission of gamma rays, and internal conversion.